All right, so now we have Simpson's rule. So the trapezoid sum provided a better approximation of the definite integral of a function that is increasing or decreasing than either our left or our right sum. And similarly, the midpoint, which we also have looked at, that's the going from the midpoint here. So we're taking the average of them and we're actually coming up to here. So it's a little bit over, a little bit under. So it's kind of the midpoint. And so what we have here is, f of x0 plus x1 over 2, x1 plus x2 over 2, and f of xn minus 1 over xn plus xn over 2, and then all times are delta x. So that's going to be a better approximation of the definite integral from a function that's increasing or decreasing than either the left or right. But how do our our trapezoidal rule and our midpoint compare? Well, a midpoint sum rectangle has the same area as the corresponding tangent line trapezoid. Think about that. So our midpoint is here, and the tangent line is going to be always above. Whereas before, it was just wherever it happened to be. Sometimes it was below, sometimes it was above, depending on how the shape of the curve was. All right. It appears from figure three then that we can be proved in general that the trapezoid sum error is about double the midpoint sum error when the graph of the function is concave up or concave down. So it looks like it's, double it. And if we wanted to actually calculate it, we could, but we're just going to take their word for it and not worry about that. So this suggests that a weighted average of the two estimates, the midpoint and the trapezoid, would be kind of the way to go. And remember, the midpoint being counted double the trapezoid sum. So we're going to take 2 times the midpoint plus the trapezoid, and we're going to divide by the total, which is 2 plus 1 or 3. Okay, so this hopefully then weighted sum is going to be a better value, and this is called Simpson's rule. Now, to simplify the notation, we agree to divide the interval into two n equals subintervals when Simpson's rule is applied. So if n is equal to 2, for example, it's going to be divided by 4 equal subintervals of length delta x. So we're going to go from x0 to x4, and a and b are endpoints. Now, there are two equal subintervals for m2 and t2 equal length of 2 delta x with endpoints. We have a to b of 0 to 4. And so, therefore, we have m2, since we're using n as 2, is just f of x1 plus f of x3 times 2 delta x. T2 is f of x0 plus 2 f of x2 plus f of x4 times 2 delta x divided by 2. And so using this equation up here with all that stuff, we end up with S4 for Simpson's rule is f of x0 from here plus 4 f of x1 because, we have so many of them, and plus the 2 f of x2 plus 4 f of x3 plus rather f of x sub 4 all times delta x divided by 3. Now this is, s of 2n, so n of 2, 2 times 2 is 4. That's why we have that. And nice thing is Simpson's rule always requires even number of subintervals, and that's because it's that 2n up here. As we see right here, we have s sub 2 times n. So it's always going to be an even number of subintervals. So stated in a simplified rule, f of is going to be some function defined on an interval from a to b. We're partitioning that interval a to b into 2n subintervals with equal lengths. So we take b minus a divided by 2n. And so we're going to get those intervals. So then s of 2n is going to be f of x0 plus 4f of x1 plus 2f of x2 plus 4f of x3 plus 2f of x4, and so on down to 4f of x2n minus 1 plus the f of x sub 2n times the delta x divided by 3. And that's going to, again, approximate that. So this should be better value than if we did even the trapezoidal rule. So using Simpson's rule with n equals 2 to approximate the integral from 2 to 10 of 1 over ln of x dx, and we're around the function values and all that stuff. So again, we have, in this case, 2n is equal to what? Well, we're going to divide it into 4 parts, okay? So if we're starting at 2 and we're going by that to 10, we're going to go 2, 4, 6, 8, 10. So we're going to have 4 parts. And so that's our x's, so our f of x is here. And again, I'm just going to plug in the values all the way, and then I can rewrite them with only the 4 decimal places. So that was 1.442695. This was 0.9, oops, 7. 0.7213475. This was 0.558111063. This was 0.48089835, I think. And then 0.43429444. And we'll just leave it at that. All right, so going from there, what we need to do is we need to plug it into our function, and we're looking at S4. Okay. Well, we take our first number, and we're only going to do 4 decimal places. So that's going to be what? 1.4427 plus. Now we take 4 times the 1, and so that's going to be a 0.7213. Now we're down to 2 on the next one. That's going to be 0.5581. And then we're going to go back up to 4 times the next one, which was the 0.4809. And then we're going to go back down to just only the last one, which was 0.4343. And then we're going to take that times, and in this case, it's going to be our delta is 2 and divided by our 3. Okay, so times 2/3 basically. And again, for sake of taking and plugging in things, hopefully you can do that. And we should get 5.20 when we round to 2 decimal places here. Okay. All right, so hopefully that helps a little with Simpson rule, and then we'll come back for some more from other things.